So today we're going to be starting off with exercise 10.2, worked example 1. I'd like you to try to draw the diagram first, so if you could pause it now and have a go. Now, I've already highlighted the important information. A particle is in equilibrium that is acted upon by three forces. One force acts horizontally. So I'm going to start by orientating this information on a diagram. One force acts horizontally and has a magnitude of 5 newtons. Now we're going to call this force 1. Another force acts at right angles to the first force and has a magnitude of 6 newtons. Now I'm going to call him force 2. We want to determine the third force, which is going to be acting somewhere down here. Okay, now this diagram is important because we've orientated it going in positive directions, but there is no reason why I couldn't have drawn it as going along this way on the horizontal axis for 5 newtons and going down for 6 newtons, which means that our counterforce will be going in that direction. Or I could have drawn it going that way, still having that going up, which just means that your counterforce will be going in that direction. Now, the important things to note here is no matter how you draw this diagram, the angle between this force and that force, so the angle between your 5 Newton force and your resultant force, F3, is the same in all of these diagrams. Okay, it also will have the same magnitude in all of the diagrams. So when we're looking to solve these sorts of questions, we want to find a direction, we want to find a magnitude, and then we want to relate that direction back to one of the axes. Now, it doesn't matter whether I relate it back to the 5 Newton force or the 6 Newton force, just as long as I state what direction it's going in, whether it's clockwise or anti-clockwise, and which force it's related to. Okay, so the first thing that we're going to note is that if it's in equilibrium, that means the sum of these three forces is going to be equal to 0. Now, I'm going to start by defining my forces. So I've called this axis F1. It wouldn't matter if I called it something different. And it is 5I because it's only going across in this positive direction. Okay, force 2, for the same reason, is going to be 6J. Okay, it is 6 units up, only in the y-axis. F3 then is the one that we are trying to find. So 0 is equal to F3 plus 5I plus 6J. Now to find F3 on its own, all I'm going to do is take these parts over to this side by making them both negative. That's going to leave me with F3 is equal to negative 5I plus 6J. Okay, so now that I've got that, I can start looking for my magnitude and my direction. Now the magnitude of force F3 is going to be equal to the square root of your x component squared plus your y component squared. Now, when I square those, if I put brackets around it in my calculator, it will do it for me. Otherwise, I just need to know. Minus 5 squared makes 25. Same thing for this. Down here, 36, which will give me the square root of 61. So the magnitude is the newtons. Okay, it's the length of this line here. Next thing we're going to do is we're going to look for the angle that it makes with the x-axis. So if I put my little dotted line in here, I am calculating this angle from the x-axis down. Now I'm doing that just to try and make it a bit more standard so that you can just, throw some values in. Because I know that if I'm looking for the angle it makes with the x-axis, it's going to be the y component divided by the x component. So in this case, tan negative 1. The y component is negative 6. That should be a negative there. Divided by negative 5. When I pop that in my calculator, it's going to give me 50 degrees. Now, you can go to the decimal place, that's fine as well. So, like I said in the beginning of the video, now we have to orientate it to one of the axes. If I want to make it in relation to this 6 Newton force, I can do 90 degrees plus the angle. If I want to make it in relation to the 5 Newton force, I can do 180 degrees minus the angle, and that's going to leave me with this angle in here. Okay, so that's what we're going to do. 180 degrees minus the angle equals, now this will be travelling in the clockwise direction, from the 5 Newton force. So 180 degrees minus 50 degrees equals 130 degrees, clockwise from the 5 Newton force. So if you're thinking about this in terms of the diagram, here's my 5 Newton force. I need to go this way for 130 degrees, and then when I do that, that's where I'll find my resultant force of F3. Okay, next question. A particle is in equilibrium. Now again, as soon as I see that, I know that means that when I add them all together, they should equal 0. So they're in equilibrium. It's acted upon by 3 forces. The first force acts horizontally and has a magnitude of 5 newtons. The second force has a magnitude of 6 newtons and acts at 60 degrees with the first force. Determine the third force by the sum of vectors. So we're going to start with our diagram again. Now I'm going to draw it going this way, 5 newtons. Okay, so that's my first force. F1 is equal to 5I. Now, this second part over here is changing our diagram slightly. So it's saying it acts at 60 degrees. So if I put it up in this positive section, that just means both components will be positive. If I put it down here, that means that my I component will still be positive, but my J component will be a negative. Doesn't matter what you do, because you're still going to relate it back in the end in terms to what angle it's acting on one of the forces. So here we go. There's my second force, 6 newtons, and that is 60 degrees. Now, if you think about this 6 Newton force at 60 degrees, I can break that down into the I component that it is by saying cos, or 6 cos 60 degrees I plus 6 sine 60 degrees J. Now, if I'd chosen to put that force below, this J component would be negative. So that's the only effect it's going to have. It's got a 6 in the front because the hypotenuse there is 6. So I'm going to use my exact values for this. Cos of 60 is a half. So 6 times a half will make that 3I. And sine of 60 is root 3 on 2, which will simplify with the 6. So it will just become 3 root 3 J. Now, the third resultant force that we're going to find will be coming off in this direction somewhere because it's counteracting these forces, so they all equal 0. So 0 equals F1 plus F2 plus F3, where F1 is 5I plus 3I plus 3 square root 3J plus F3. First thing I'm going to do is I'm going to group my like terms here. So that's 8I plus 3 root 3J plus F3. And now I can take this one to the other side. Now, normally that would make it negative, but instead I'm going to divide the negative over now so that I don't have to do an extra line of working because I'm running out of space. So everything in this bracket will become negative, and I just need to expand the bracket out. Okay, so now I've calculated the vector that results from this for our third force. I'm going to do the same steps again. I'm going to calculate the magnitude of it to work out what the force is. So, square root of 8 squared plus the plus 3 root, or negative 3 root 3 squared, which is going to turn this into the square root of 64 plus 3 squared is 9 times 3, 27, which is going to give me the square root of 91. And that is a Newton force. Okay, next thing we're going to do is we're going to work out the angle that it's acting on. Now, again, I'm looking at the angle that it's making with the x-axis, so I'm going to be looking for that one in there. So tan theta equals y over x. So then theta equals the inverse of tan. And our y component for our third force is -3. -3 root 3 divided by -8. Now, when I put this in the calculator, it's going to give me an angle of 33 degrees. So, next thing I need to do is work out what angle this is acting with in relation to the other things, because I now know that this inside here is 33 degrees. So if this one is on the axis, I can do 180 minus the 33 degrees, and that will give me the direction that it's traveling in the clockwise direction. I could also do, let's see, 30 plus 90 plus the angle, and that would give me the angle that it's acting in with the 6 Newton force. So it doesn't matter what you do. I'm going to do the 180 minus the angle, and that's going to give me the clockwise direction. From the 5 Newton force. Okay, so 180 minus 33 is going to give me 147 degrees. So this thing is acting with a force of a square root of 91 newtons at a direction of 147 degrees clockwise from the 5 Newton force. So if I redrew this diagram with that 5 newtons going that way and my 6 Newton force going that way, and that's 60 degrees in there, it means that over here at 147 degrees clockwise from the 5 Newton force, that's where that force is acting.